Hello and welcome to the Rustacean Station. I'm your host, Alan Wyma. Today I'm with Gray Olson, who is a programmer at Embark Studios and also the creator of Presser. Welcome.
Thank you so much. It's great to be here.
Yeah, why don't you tell us a little bit more about kind of what you're doing and more about your history, right? Because you're like me, you're expat, I guess you could say.
Yeah, I am. I was originally from Phoenix, Arizona in the United States, and I recently relocated out here to Stockholm in Sweden. I currently work at Embark Studios. I have for just over 2 years now. I actually come from sort of the Rust open source and especially sort of open source game dev community. I previously, before I was at Embark, contributed to a number of the sort of early Rust game dev engines and especially graphics libraries. So I contributed to GGEasy and GFX-RS and Amethyst, which is sort of how I ended up at Embark in many ways. And so now I'm working on, for now at least, private game dev things in Rust and doing sort of open source things both for work and on the side, which Presser is one of them. Yeah.
Can you please pronounce that name for me? Is it called Amethyst? Is that how to say it?
Yeah, Amethyst. It's like the sort of precious purple gemstone.
Yeah.
Yeah, it was, I mean, it still exists, but certainly less steam than it once had. A Rust game engine that was sort of the first big, ambitious, data driven, data oriented game engine project in Rust. I think, unfortunately, several of its sort of key contributors had life things happen at similar times, and that also coincided with the launch of Bevy, and so much of it's sort of translated over there. But it served as some really important sort of foundational and exploratory work for game development stuff in Rust. So, yeah.
Yeah, that's what I understood is like one of the first most popular like open source game engines, and I think now it's like there's no feature development, but maybe some code security fixes or something like that. I'm not too sure what the status is exactly.
Yeah, I'm not 100% sure on exactly what the status is. I think there might be a little bit of feature development going on. I know there are still a few people that use and enjoy it, but I think certainly not as much compared to, I guess, its heyday. Yeah. And I think in general, it's sort of in maintenance mode more than active development mode.
Yes, I see you're on the rendering team, and you're also on the rendering team at Embark Studio. So rendering team means like anything visual, or how would you say that?
Yeah, I mean, I usually describe it as we write the code that for every frame in the game figures out the color that every pixel on the screen should be based on the simulation. So, all the things, that includes grabbing all the necessary data, putting it into the necessary places, sending it to the GPU, telling the GPU what to actually do, which things to draw, and then also how to draw them. And yeah, it's a pretty wide field, which is one of the things I really enjoy about it. There's a wide variety of sort of different interesting problem areas to work on. And also the fact that rendering is, I mean, like, point of it is make pretty pictures. And I come from an art background. I actually have a BFA in drawing and painting rather than computer science degree. And so I really enjoy using code as sort of like medium to create art in many ways. And I think graphics programming allows you to do that.
Yeah, I saw your website, and you definitely have a very big art background. So I'm just trying to understand because most of the art people I know, they, of course, they know their ways out of these graphic programs and, like Adobe and all that stuff. But when it comes down to maybe writing some simple code or doing some simple math, it's just like way out of what they say they can handle. I don't know what the truth is, but
Sure.
I mean, like, do you just have like two sides of your brain that's able to function? Because for me, I can barely draw a stick figure. Like my writing is horrible. I don't write anymore. I don't write anymore. I give it to my wife. I say, "Can you write this for me?" Because if I write, they cannot understand it. Nobody can read it. That's worse than a doctor. So I don't know how I even passed the first grade. So I'm kind
Yeah.
of curious about how you can do both sides.
I think perhaps I have somewhat of a unique brain, I guess, but I think, in my opinion, is that people sort of sort themselves too early into categories that are like sort of socially enforced in terms of like art versus, right side versus left side of the brain or whatever. I think a lot of people who are enjoy or are good at the arts get turned off of sort of like math and science at an early age because of sort of mediocre teachers, and then sort of just decide I could never do that, when the reality is that like they could. They're totally smart enough, and it's not like there's anything super special. It's just the fact that, like, I think especially math and science, you know, they build on foundations all the way up. And so if you decide at an early age, or you have a bad teacher at an early age, and you're just like, well, I suck at math, I can't do it, you're not going to learn the foundations, and then you're going to really struggle as you try to build on that. And like the kinds of math that you need to do, like say graphics programming, are, relatively high level. I mean, anyone can learn them, but if you sort of decided to stop caring about math at a pre-algebra level, then it's going to take a while because there's just a lot of stuff to learn. And sort of conversely, from the other side, I think many people who are good at sort of code and whatever see their initial struggles with creative disciplines as like an inherent failing of their like, brain, when I think everyone starts out, with maybe a few exceptions of like outstanding like prodigies or whatever, as being like bad at art. And certainly I started out being bad at art, and it was sort of just a matter of the fact that I sort of kept with it at a young age, and that gave me the motivation to continue. But from a drawing and painting perspective, like I only got into it like when I was younger. I did sort of photography because that's what my dad did. But I didn't really like, I was always bad at drawing. But during high school, I was just like, you know what? I really want to be able to draw well. And so I'm just going to dedicate myself to it. And like, if you look back at my first little scribbles in high school, you'd be like, that's really awful and bad. And they were. But if you practice enough, you can get through it. So yeah, I think it's really just a matter, like, I'm not necessarily convinced that anyone is hopeless at anything. It's just a matter of actually being able to push through the fact that you're bad at it at the beginning, which sucks. It really does. And I don't blame anyone for not wanting to push through that. But yeah, I think a conclusion to this is that I think there's very valuable insights from both for the other discipline. Like, as I learned graphics programming, the sort of knowledge about the physics of light and how light interacts with objects and how that, creates the colors in a graphics programming context. Well, that's all knowledge that directly translates to trying to paint something. Like, how do I make a surface look like I want it to under this lighting conditions? Well, I can think about how would my program try to figure that out, and it's the same stuff. So I think there's really interesting knowledge exchange that could happen in both directions, that would benefit people, and I try to facilitate that when I can.
Yeah, graphics is definitely something that can be quite interesting. Like, I'm sure you've heard of the game of, was it Conway's Game of Life, I think it's called?
Yep, absolutely.
Yeah, like that. You can make some very interesting patterns and designs with that, along with, I mean, just an annual. I mean, because you're on the rendering team, right? I don't need to tell you, you're preaching to the choir, basically, is you know all about the different crazy and interesting patterns you can make with math. And yeah, I guess they have a really weird relationship.
Yeah, absolutely. I mean, one of the things that I became super fascinated with in a few years ago, in sort of the last year or two of my college career, which I was doing, an art degree, but doing graphics programming on the side, was fractals, which are exactly like you say, are super fascinating, like mathematical constructs, but that also create these beautiful pictures. And so I sort of adapted my own little hobby renderer, which still exists on GitHub. It got moderately popular, called Rain, Rayn, like, because it's a ray tracer, Rain anyway. I sort of adapted that to render fractals, and then I would use the sort of rendered images of fractals as like a base to then paint on top of for my art classes in school. So yeah, I think there's really, really interesting ways that math can create art, and then that like hand drawn art can interact with those sort of like mathematical objects. Yeah, this is definitely an area that I find super fascinating.
Do you mind to actually go over what is ray tracing? I kind of understand, but I always hear about ray tracing whenever people talk about like, oh, just learning. Like I think even when people are doing Rust, they always talk about how like one of the first projects that they do is ray tracing, and when you want to get into video
Yeah,
game rendering, ray tracing is like the first thing you do. It's like the hello world that I understand of video game rendering development.
yeah, absolutely. So ray tracing it's a slightly simplified but still pretty good simulation of how light actually works in the real world. So the point of it is that you have some sort of objects in a 3D scene, and you have some light sources in that 3D scene that emit light, and then you have a camera that captures light. And so the point of ray tracing is to actually simulate rays of light that are emitted from light sources, bounce around in the scene off of objects, and then eventually reach the camera that is looking at the scene. And so ray tracing is this like beautiful algorithm or set of algorithms really, because there's many different ways to do it, that is super intuitive. Like you can totally think about, oh yeah, this light is like bouncing off of things and then, going from light source to the camera. And it's also not particularly difficult to write a program that does this. There's a great series of books called Ray Tracing in One Weekend that I think many people have done in Rust as sort of like their first weekend of project, which is really cool. It's also how I first started ray tracing. And so, yeah, that's sort of the core of ray tracing. Now, there's many different sort of like sub algorithms. What I described is actually one specific case of ray tracing called path tracing. But yeah, all ray tracing techniques essentially revolve around shooting rays into a scene and calculating the light intensity as light, sort of travels across that ray and intersects geometry in the scene. It's really interesting because this is such like a simple concept and relatively simple to implement, but it relies on sort of like some pretty advanced foundational math, like to actually prove that it's correct. It makes intuitive sense, but actually proving that it's correct is difficult. And also, it's incredibly like computationally expensive. It's super simple to implement a basic ray tracer, but it'll take, 20 seconds to render a noisy version of your scene. In video games, we want to render a frame in a few milliseconds. So has been sort of the problem with ray tracing since it was sort of invented, I think back in like the 80s, is that it's beautiful and it create very much simulates what actually happens in the real world. So it can create, very photorealistic images. But it's so hard to compute that it's been prohibitively expensive to use. For a long time, it was prohibitively expensive to use in even movies. And only recently have both sort of algorithms and computational power gotten to the point where we can just start using it in video games a little bit.
Now, I'm kind of curious, right? In my thought process, I'm thinking rendering a frame is probably the most expensive thing to do in a video game, no?
It depends. In terms of a single, I mean, if you can view rendering a frame as like a single piece of work, then in many cases it probably is the most expensive thing. But it totally depends on the game and on the quality of graphical rendering that's happening. If you imagine a game that is like, say, a game like StarCraft 2 or like Age of Empires or something, where that you're simulating, or like, cities, skylines, The Sims, something like this, where you have thousands, hundreds of thousands, millions of like independent actors happening in the world every frame, and the rendering cost is only rendering us a fraction of that, then it might be that the sort of computational cost of calculating, simulating the world is actually greater than the cost of rendering it. But in the game, like, for example, I don't know, let's say Portal 2, the rendering is, at the time at least, the rendering would be more expensive than the simulation because there's not that much happening. Although maybe that's not the best example because physics is actually one of the most computationally expensive things, and Portal heavily relies on physics, but you get the point. In certain games, more time will be spent rendering than simulation and vice versa. And ideally, you want to try to keep these two costs sort of like in harmony because much of the cost of rendering is happening on the GPU. And the GPU can execute basically independently of the CPU. So if you can keep the cost of rendering a frame and the cost of calculating the next frame around the same time, then you can keep the graphics card and the CPU fully working at to the optimal degree. Whereas if you can't keep those similar, then you'll have one sort of just like waiting around for the other one to finish, which is not ideal.
Yeah, I was thinking of a game like that. I mean, if you're rendering sprites, probably not too bad unless you have to do like some major scaling, etc., or these kind of manipulations, things like that.
Yeah, interestingly, sprites can actually get more expensive than you'd think pretty quickly because of like memory bandwidth requirements. And like 3D graphics pipelines in games are like so sort of hyper optimized in many ways that it can be surprising how little relative cost there is to rendering 3D objects compared to like just sprites, at least in sort of modern graphics pipelines. But the intuition is correct. Generally, I mean, sprites are not going to be a huge issue.
Especially like if you're doing vectors, etc., right? Those are not too bad. Or that's something else, right? A vector would be something
Like
you
vector
scaled it right.
graphics and
Yeah. Vector graphics, I mean, they scale nicely, right? Because it's basically all math, if I understand.
yeah, although actually nicely rendering vector graphics is a super hard problem on the GPU and it can be super expensive, which is why in games usually we don't directly render vector graphics. We first quote unquote rasterize them just into a texture and then just draw the texture later because yeah, current algorithms for sort of actually you have to think about a vector graphic is essentially just storing like information about the sort of bounds of an object. And so because of that, you get these really nice properties where in theory they're defined at like any scale and they're also incredibly highly compressed, so the amount of data needed to describe this shape is very small. But the downside of that is that it's actually really difficult to figure out, okay, well, I have this like complex set of shapes that make up this overall shape, but how do I figure out whether this pixel is actually within the shape or outside of it, especially if I'm at the edge of the shape? If I don't want it to look aliased and like just stepped sort of pixely edges, I have to calculate, anti-aliasing, edge filters and stuff. And doing all this sort of on the fly can be super expensive. There are some libraries that do it really interestingly. I think there's one by a guy called Eric Linyel. I probably butchered his name, but it's called Slug, and it does this in pretty quickly in the GPU. But traditionally, the method that we use instead is that GPUs are super highly optimized for triangles. So what we do is just rasterize the shape once into a texture and then just draw one or two triangles and sample the texture because that's what GPUs are good at. And it's sort of, it's saying we only have to do this expensive operation once and then we can just do the cheap operation many times.
Yeah, I would love to. Do you think you can simply explain why is it that you can use triangles to draw anything in this world? Because this is what I heard, and this is basically, I mean, they're polygons, right? It's basically when you hear polygons, you're talking about every single triangle you can use to draw some kind of shape, right?
Yeah, I mean, the simple answer is basically just, I mean, you can use triangles to draw any shape by just making the triangles smaller and then adding more of them so that it closer and closer approximates the thing you want to draw, which is what we do. So there's no sort of like magical trickery. You really are just drawing triangles. The thing that makes triangles nice is that when you have a triangle that's defined only by 3 points, you know that that triangle is always planar. So any sort of like point on the triangle is always planar with any other point on the triangle. And so that has some really nice properties when you think about, and also there's various other similar sort of like properties of triangles that mean that you can easily interpolate things across a triangle in ways that are not well defined. For example, like a quad, like a square. If you have any set of 4 points, they may not all lie on the same plane. Whereas with a triangle, if you have any 3 points, it always makes a plane, a triangle in a single plane. And so that's why we sort of used triangles. It's like the most basic shape that has like a 3D form. I guess really it's a 2D form that exists in 3D space. And so because of that, we have some really nice properties that like you can just arbitrarily add more triangles and get more detail to approximate the shape you want to draw, even though you'll never actually get to exactly the shape you want to draw without infinite number of triangles.
So obviously, yeah, the more triangles I have, then the more of the shape I could properly render, but I can never be theoretically I can never be 100% on par, right?
Yep, exactly. There's a little bit of nuance in that, like, you'll never be 100% accurate by just using triangles, but there's the interesting property that in graphics, we're not just concerned with, like, we're not only drawing triangles in terms of when you draw a triangle on the GPU. The point of that is to eventually you get back sort of a set of pixels that triangle sort of overlaps on the screen. And then you still get to decide for each of those pixels what color they are. And so you can do some clever trickery where it's not like you have to paint in every single triangle a single color, in which case, exactly what I said before would be accurate. You'll never get to the exact shape. But if you can just use triangles as sort of like an acceleration, and then you just use the fact that you now only have this small set of pixels to decide the color of, you can then exactly decide the color of each pixel and get, in theory, exactly the correct result. I'm being intentionally vague here because this is highly dependent on what you're drawing and how you're doing it. And also, this is very GPU centric. Like, we also use triangles even outside of the GPU context to define meshes to ray trace often because they have those same nice properties. But in terms of like on the GPU, you can do a bunch of trickery.
I heard that a lot of the math for like GPUs is like matrixy math. Is that right? Matrix math? Is that how it usually is?
Yeah, so I mean, I think the way you should think about a GPU is just like a CPU with thousands of very low performance cores. So it can, in theory, execute essentially arbitrary code. But the thing about matrix math is that a sort of quote unquote embarrassingly parallel problem, in that if you set up your data correctly, then you can have the GPU calculating like thousands of these things at the same time and all sort of like independently of each other so that they don't, each little CPU core doesn't have to talk to the ones that are every other one and sort of communicate, which would destroy performance. That's sort of why we use matrix math so much in GPU code. And then there's also the idea that matrix math is absolutely a fundamental building block of computer graphics in general. And that's because like linear algebra is used in this context to do like represent all of the things that we want to render in 3D space. It's just a way to think about the representation of an object in sort of a way that we can talk about and reason about and operate on mathematically. So, like a matrix in computer graphics, you can essentially think of as just like encoding the transformation of something. And a vector can encode either a direction or a point. So there's much more nuance in many of these things as well. I have a math library called Ultraviolet that, in the process of writing it, I sort of discovered and came to enjoy a thing called geometric algebra, which is somewhat akin to linear algebra, but approaches things even more from sort of a geometric point of view. And doing so can sort of let some really beautiful and elegant math fall out of just sort of very simple first principles that can help us do better transformations and things. So, for example, you may have heard of a quaternion, which to many people in sort of game dev is this weird thing that just means a rotation, and I don't know how it works, but I tell the API to do the rotations and it does it, and it has like better properties than just saying X, Y, and Z rotation or something. And geometric algebra has sort of analogously the concept of rotors, which are quaternions, and quaternions are rotors. They're sort of just fundamentally formulated like from a different starting point that is much more intuitively easy to understand. I won't try to do so in an audio only podcast, but hopefully, if anyone is interested, they can sort of jump off of that. And yeah, so I think I went on a bit of a tangent there, but there you go. That's where we get sort of matrix math from in computer graphics.
Uh, Kind of going back to something you said earlier as part of the rendering team, I think you alluded to something about basically what Pressor's doing where you're copying data, say from the CPU or maybe even from memory straight into the GPU, right? Isn't that kind of where Pressor comes in?
Yes, that's definitely one of the sort of primary use cases we're using it for at Embark right now. And it was the motivating use case for its creation. The idea is that oftentimes in sort of graphics APIs like Vulkan, etc., but you can also get this if you're working with just very low level unsafe code on the CPU. You'll allocate a raw piece of memory that, after allocation is still uninitialized. And so because it's uninitialized, working with it is more complex than it otherwise would be. I mean, in purely safe Rust code, you'll never directly work with uninitialized memory. The only sort of like way that you can interact with it is if you declare a sort of variable without immediately assigning to it, then that, variable will be uninitialized until you assign a value to it. And you may notice that, Rust will not compile, it won't let you read from a variable that you declared until you initialize it. And if it can't prove that you always initialized it, then it won't compile if you try to read from it. And so Presser is sort of a way to allow you to do that at a lower level that is not sort of because when you allocate a raw buffer and then you have that memory back directly, you're in a very sort of unsafe state, and interacting with that memory is somewhat difficult to do in Rust. And so Presser tries to help you do that in a better way, in a more obvious way. Yeah.
I'm just trying to follow, right? So sadly, I don't have the opportunity to use Rust full time yet. I'm looking for excuses. Because, I mean, what I'm thinking about in my head is just a normal, lonely programmer is if you want to copy something, you're going to have to first initialize enough memory in order to do that, and then you can copy it over. So I'm having a hard time to understand what Presser is doing and why would I need it if, like you said, I mean, I have to have enough memory and I have to have everything kind of ready. It's hard for me to really understand. Maybe I missed something. Do you mind to maybe speak to me like I'm, as they say, speak to me like I'm 8 to make sure I
Sure,
understand all
yeah.
this?
So one thing that's key to understanding why Presser is necessary is understanding sort of the concept of uninitialized memory. So, uninitialized memory is a sort of meta state about a piece of memory. So, when you allocate memory for many reasons, many performance related reasons, um, the memory starts in a state that's called uninitialized. Now, this is not simply a state where, you know, many people when they first hear about uninit, they think, "Oh, that means there is memory there, but maybe it just has like junk values from like some previous allocation. We haven't like written our own stuff into it yet." But in fact, that's not what uninitialized memory is. And there's a very fundamental difference here. I think it's important to here introduce the concept of sort of talking about what the language virtual machine, in this case, the Rust virtual machine, does versus sort of like what the hardware does. Because talking about what the hardware does is essentially meaningless because in order for the hardware to actually do anything, the language and the compiler has to actually tell it to do things. So what the hardware does can inform what we define the Rust virtual machine as doing, but in order for something to make sense, we have to talk about what the Rust language thinks about it. So, what's the Rust virtual machine? It's basically just sort of like the way we talk about thinking about what the Rust language does, like what operations can it perform and how does it perform them. So, you've probably heard the term undefined behavior before as this sort of very scary thing. And it is. But the reason is because if the Rust virtual machine specifies behavior as undefined, then it can do anything there. And that allows it the flexibility to optimize things. And uninitialized memory is an interesting case of this. So you can think of uninitialized and memory being uninitialized as like a piece of metadata that the Rust language and compiler stores about a piece of memory at compile time. So, every byte could have the values 0 to 256, right? Each bit could have an individual value. But each byte also at compile time has an extra state. It doesn't have 256 states, it actually has 257. And the 257th is being uninitialized. And the thing about that is that uninitialized memory could not exist at all. The compiler is free to treat it as if it does not exist at all. And by doing so, we get some really interesting opportunities for optimization. But we also get some behavior that would be surprising at first. So, with that said, when you first allocate memory, the memory that is passed back from the allocator is marked as uninitialized, which means that as of that time, that memory might not exist at all. The compiler is free to treat it as if it does not exist. Only once you actually write a value into a byte of memory does it become initialized, and then the memory actually has to exist, and it actually has to have a value between 0 and 255, each byte does. So, when you get memory back from an allocator, it starts as uninitialized. When you write to it, it becomes initialized. Why is this important, or how can this go wrong? Well, I'll try to describe a sort of contrived case here. Hopefully you can understand it. Let's say you have a function that, as its input, takes a single Boolean value that is called is in it. In the function, the first thing you do is you allocate some memory that starts as uninitialized. Then you check the value of the Boolean that was passed in, and if the value passed in was true, you write data into that uninitialized memory and save it into that memory. Then you check the value of the pass-in Boolean again, and if it was true, you print the line initialized to the console, and if it was false, you print the line uninitialized to the console. And then after that it's if statement, you finally unconditionally print the data that you wrote to the uninitialized data. So the compiler knows, in this case, that reading from uninitialized memory is illegal. It's undefined behavior. So it can then prove that if the program does not have undefined behavior, which it must not, then the only way for the program to not have undefined behavior is if the passed-in value is always true, because we only write data into the uninitialized buffer if it was true, but we always read the data back out of that buffer, no matter whether it was true or not. So therefore, the compiler thinks it must always be true. It can prove it must always be true if the program doesn't have undefined behavior. So in this case, the compiler is actually free to optimize the function down, completely optimize away all of the checks of the Boolean value passed in, and simply only print the line initialized to the console and then the value that you wrote into that memory. And so if you ever tried to pass the value false into this function, then you would get the result of it just always printing initialized, and it would always perform as though you passed true into it. And thus, through calling this function in other places, you can have behavior that simply just doesn't make sense. It's undefined because the compiler tried to optimize this in a way that is entirely legal based on the rules of the language virtual machine. But obviously, it results in completely unexpected behavior in, from a programmer's point of view. So this is an example of why uninitialized memory is not just any bit value, because if it was just any bit value, then this function would work probably as the programmer would expect, which would be that if you passed the value false in, it would print uninitialized and then just print some like junk data as the uninitialized data. But because it's uninit and that's a special value that doesn't just mean any bits, the compiler can actually completely remove all of this because it can prove to itself that there's no way for anything else to occur in a valid execution of the program. And so this is the sort of thing that we want to avoid by not wrongly interacting with uninitialized data. There's sort of another level of nuance here, which is that there's a few more levels of nuance, but for now, the next sort of one that I want to talk about is that LLVM, the sort of optimizing compiler that Rust is built on top of, has these things called attributes that you can apply to values that sort of guarantee to LLVM that certain properties about that value are true. And one of these attributes that you can apply is called no undef, which guarantees to LLVM that there's no undefined or no uninitialized memory in that value. And in fact, in the past, LLVM would perform some really important and sort of fundamental optimizations, sort of just assuming this was the case, because the undef attribute didn't yet exist or it wasn't yet applied to that. But as LLVM has upgraded, I don't know if you've followed too closely, but actually over the past few versions, in some cases, performance has not actually gone up. It's either sort of stagnated or gone down. And that's because some optimizations have been guarded behind attributes that make them actually be sound. But that also means that if those attributes are not or cannot be applied to something, then those optimizations don't happen. So for example, even just a optimization that's as simple as taking, x times x is equivalent to 2 times x, that's only valid if x has no uninitialized values or is not uninitialized. There's only a valid optimization. So that optimization is now guarded under no undefined in LLVM. So in order for us to take advantage of these optimizations, we have to be able to prove that a valid integer, like an integer value, has no uninitialized memory. Thus, Rust defines even for a U8, which some people probably are thinking, oh, what's the problem? A U8 is valid for any value. Well, yes, it's valid for any value, but uninitialized is not a value. It's a separate thing. And so, even for fundamental integer types, it is still invalid to have an initialized memory as a value of a basic integer type. Yeah, I went on a bit of a monologue there. Let me know if I lost you or if you're understanding or what.
Yeah, I'm somewhat understanding, right? I'm aware that there's a tiny runtime with Rust, but I mean, compared to like JVM, etc., it's very tiny.
Sure. So I guess to be clear here, the Rust virtual machine that I'm talking about isn't a runtime. And in fact, the status of a piece of memory as uninitialized or not is not tracked at runtime. It's tracked at compile time. So at runtime, Rust, doesn't treat, it doesn't keep track of for every byte of memory, whether it's defined or not. It simply instead at compile time keeps track of whether these pieces of memory have been initialized at a certain point in execution flow, and the compiler uses that knowledge to be able to perform compile time optimizations where, that example that I was talking about before, where the function, it just completely removed the case where the Boolean value passed in was false. Thus, in the compiled binary, there literally would be no instruction for checking that Boolean. It would simply disappear and it would just always assume that it's true because the compiler could prove to itself that that's the only valid thing for it to be. So, when I'm talking about the Rust virtual machine, I'm talking about just sort of like the theoretical framework that the Rust, language team programmers sort of use to talk about how Rust works, not actually a runtime that is being executed at program runtime.
Okay. All right, I got you. Now I understand.
Cool.
Okay, the part that's still maybe you might have addressed this, but maybe I just couldn't quite get it right. So when I'm copying the data, you're saying that there's a chance that I just didn't quite get the part about the uninitialized part of data that I need to be copying into. To me, you just always initialize it, then you copy into it because you have to make sure that you have it because you need to ask the OS to give you the memory first.
Yes.
But you're talking about when you're not using the default allocator or when you're copying to something that doesn't have an allocator. Is this what I'm understanding?
No, not quite. This is definitely a subtle point, so I'm glad we're kind of going into this, which is so even when you're using the default allocator or when you allocate something and the OS, the allocator returns and says, "Okay, I've allocated this memory for you." There's sort of two pieces here. One is that memory, even once the allocator returns it to you, starts out as uninitialized. If we want to actually make it fully initialized, we have to write a value to every location in that memory, which can be expensive. But in some cases, it is the sort of like thing that we do. For example, in the Rust standard library on the vec type, if you want to grow the size of a vec, the only safe way to do that is to either push in values to the vec individually or to create some sort of default value and then sort of copy that default value and write it to every location that you're sort of expanding the vec into, which in some cases could be 0. So that's how you get like zeroed memory. That would be, okay, if I zero memory, that means that not only have I allocated the memory, but I have fully initialized it. I've written a value to every point in the memory, which is just all zeros, but it's still writing a value, it's initializing it. But that operation of actually writing zeros to every location in the memory to initialize it is expensive. And so sometimes we want to not do that. This is when you're writing a low level data structure and you're writing extremely performance sensitive code. You want to, especially, let's say you allocate memory and you know that you're just going to overwrite all of it with data, which is a very common case in graphics programming. We want to allocate space to then just write a whole bunch of like floating point values that contain matrix values or vector values. Well, it's a waste for us to first allocate the memory, then zero it, because we're just going to then overwrite all of those zeros with the values we actually want to write into the buffer. So instead, we want to be able to skip that zero step and just write directly the values that we want to write into the uninitialized memory in order to initialize it. I mean, in Rust, you're already doing this. You're sort of like hidden doing this every time you initialize like any value, but in particular, a value on the heap is the most direct sort of comparison here. Like internally, what it's doing is it's allocating the memory, and then instead of zeroing the bits and then copying the data into it, it just copies the data into it, and that's how it gets initialized. So the reason that we have to actually write a value to make it initialized is the motivation for this is the performance sort of optimization possibilities that it allows that I would give one example of before, but there are many. So yeah, hopefully that makes sense in terms of sort of reiterate like when we get memory back from the allocator, from the OS, the allocator has only promised us that there is the possibility of that memory existing. But in order to actually make that memory exist, guarantee that it does exist, we have to tell the system to write a specific value into it before we actually write a specific value into the memory, the compiler is free to treat it as though that memory simply did not exist at all. The OS is free to treat it as if that memory does not exist at all. So only once we actually write a value into the allocated memory are we able to confidently say that it exists and that it has some specific value that we wrote into it.
Okay, I got the part about the zeroing and the default. That part is clear. The thing that's not so clear for me is about the undefined behavior. So, is it that like you would say, okay, give me X amount of memory for this kind of data type, and then you try to read from it, and you talk about this kind of undefined behavior where you don't even have anything yet? I mean, this just could be leftover data from some other data type.
So it could be, or it could just not exist at all. I mean, like,
Okay, like you said, yeah, you could say, give me this, and it says, okay, here you go. And like you said, if you didn't use it, that then you don't have guaranteed that you have actually have the data yet.
yeah. So in that specific case, like, let's say you allocate memory, you don't initialize it, and then you read the value. Well, since that can never happen in a valid program, the compiler can just delete the allocation, delete the read, and pretend that never happened because based on its, well, not pretend that it never happened, assert that it never happens. Make the program never do that thing because under sort of valid rules of the language, it could never happen. You can't read undefined data. So any sort of operations that lead to that, it can just assume never happen and delete them entirely. So I think perhaps the thing that is a little bit unclear here is another level of nuance to this conversation, which is as of right now, the Rust reference says that a value of some type has to be valid. Okay, we won't exhaustively define what valid means, but it has to be valid at all times. It also says that a reference to any type or a mutable or even a mutable reference to any type must also always point to a valid t. So like a reference to, and then this is true even for integers, a reference to a U32 must always point to a valid U32. Now, the important part about validity of a U32 is that in order to be valid, a U32 must be initialized. That's the only requirement for a U32 to be valid, is that it must be initialized, otherwise any bit pattern is valid. But what falls out of this is that it is invalid to create a reference to an uninitialized U32 or to create a mutable reference to an uninitialized U32. While the awkward part about this is that if we want to actually let's say we create some uninitialized memory, right? And we want to write a U32 into that memory somewhere. Well, the most obvious thing to do is to get a reference to some part of that memory that we call a reference to U32 and then write a value into that mutable reference. But as the Rust, sort of language reference defines currently, that's an invalid operation. As soon as you create a reference to an invalid value, you are causing undefined behavior. Now, the nuance here is that that is still a little bit up in the air whether that will continue to be undefined behavior. As of right now, the compiler never actually takes advantage of this specific kind of undefined behavior to do anything. So it is moderately likely that in the future it will actually be valid to create a mutable reference to an uninitialized value so long as you actually write a value into it before you ever read a value from it. But let's talk about exactly what that means because there's sort of an interesting thing that what I just said brings up, which is that I said it can be valid to create a reference to an uninitialized U32, which means it's valid to create a reference to an invalid value. Now, what does valid mean then? Well, in sort of the Rust ecosystem, we've come up with in the past few years this language of safety invariants and validity invariants. So a safety invariant is basically what you think of as a safety invariant, which means that like as long as the safety invariant is not violated, safe code can't do undefined behavior. Therefore, anything that, like, let's say, within the implementation details of the standard library or within your own library, if you're writing an opaque data structure like a vec of t, well, during the internal operations of that type, you might have to do unsafe things. But as long as you don't do invalid things, you are just carefully doing unsafe, you're creating an unsafe state. But as long as you don't actually do anything invalid, that's okay. Because once you pass back execution as safe code, now the safety invariant is no longer broken, and therefore you're fine. The validity invariant, on the other hand, is interesting because it is a set of conditions that must never be broken at any time, even during unsafe code, because the compiler assumes that they are always true in order to do its optimizations. And so that is why it is invalid to ever have a value of a U32 that is uninitialized. Or, for example, it's invalid to ever have a value of a Boolean that is not either 0 or 1, because the compiler can always assume that any value of a Boolean is either 0 or 1 to be able to do comparison operations on it for optimization reasons. So, this sort of like reference to uninitialized values, there is certainly a safety invariant issue here, which is that if you try to read from uninitialized memory, you can have a bad time. You invoke undefined behavior because you would be creating an invalid value. But there's a level of nuance, which is that whether or not creating the reference itself is invalid. Right now, the Rust reference defines it as being invalid, but the standard library itself sometimes does that, and a lot of code does. So there are ongoing discussions on whether or not it should be relaxed such that it is still valid, though unsafe, to create a reference to like an invalid value, which in this case would mean an uninitialized one. That would mean then that you could take like a mutable reference to a U32 in an uninitialized buffer and just write a value to it. And that would be fine, so long as you just promised to never actually read that value before you wrote to it, because this is pushing it into the domain of safety, which is just whether you actually perform a bad action or not. Whereas validity is like you can never actually create this state in the first place. Yeah. So the idea here is, I guess the sort of main point to circle back is, let's say you create a buffer of memory, you allocate it, you have a raw buffer that is uninitialized. Okay, I want to fill it with data. How do I do that in a way that not only, like, in order to fill it with data, we are going to have to use unsafe code? Okay, that's fine. But how do we do this in a way that does not validate, or that does not break the validity invariant? And that's a different but related concern. And so Presser tries to do two things. One is that it always uses raw pointers internally, which means only uses raw pointers to uninitialized data, which means that it actually is satisfying the current validity invariant of Rust, which is that defined as being that you can never take a reference to an invalid value. Now, the sort of importance of that, or whether that actually matters in practice right now, is the answer is probably not. And also, the answer is that in the future, it will probably be, I don't want to say probably, it may be defined as actually valid to take a reference to uninitialized memory as long as you only ever write to it. There are complicating factors in actually making that happen, but yeah. The second thing Presser does, though, is that even if you disregard that, it makes more obvious that there is a safety invariant issue happening. and it explicitly tells you what you can and can't do to violate that safety invariant. So, for example, even if it was valid to take a mutable reference to uninitialized memory to write data to it, if you take that mutable reference, it is like super easy to violate the safety invariant and actually attempt to read from it before you write a value, or to write a value and then still read from it in an invalid way. Because, like, let's say you write in a type that has padding values to a buffer. Well, now the bytes where that padding exists are still initialized, even though you wrote a value to it. So then, if you later try to view that buffer as a slice of just bytes, well, now you actually have violated the safety invariant as well, because you tried to read uninitialized bytes that were still uninitialized even though you wrote a value into it. So this is why it's error prone to, even if it was or will be in the future valid to create a mutable reference to uninitialized data, it's still error prone in that you can then just pass that mutable reference to any function that accepts that kind of mutable reference. And you don't know exactly what that function is doing unless you actually do. So it's sort of hard to audit. And so what Presser tries to do is make much more explicit exactly which guarantees you have to make in order for something to not violate the safety invariant. And then also, as an added bonus, as of right now, it prevents you from violating the validity invariant that exists, even though it could be argued that right now that doesn't actually matter, but it could in the future, or maybe it could not.
Okay. You taught me a lot of stuff which I had no idea. Makes much more sense now.
Yeah. I mean, this stuff is interesting. Like, there's so much sort of like small nuance here in order to get things right, which is why Rust goes to such great lengths to sort of hide this complexity from people. Like, this is why you don't just sort of like malloc uninitialized memory in Rust as like a normal thing, like you might in C, right? Because there is so much little nuances and hard, subtle things to think about in many cases. And so, what Presser is trying to do is, for a case where you are just simply trying to copy data into a buffer, it wants to make much more clear exactly what the things that you need to uphold are, and make sure that internally you aren't violating. You know, as long as you uphold those guarantees, you're not going to violate anything. And I guess one more sort of point to make here is that one reason that this is difficult in Rust is that, like, the sort of story around uninitialized memory in Rust has evolved since the language release. Like, at 1.0, there was no way to create uninitialized memory other than to create a mutable reference to that uninitialized memory through an API called like quorum mem uninitialized. Like, that was how you got uninit memory in Rust. Nowadays, there's the type maybe uninit t, which tells the compiler, okay, there might actually be uninitialized memory here. And so this is sort of like an active area of like discussion and research within the Rust language, which is why, you know, there are some rough edges of usability here. And so that's why many people in the ecosystem have sort of just taken the path of least resistance, which is not always actually correct or good in this case. And so that's why I created Presser, because especially game devs and people like this who are chasing, you know, the sort of micro optimizations and are used to just calling malloc and writing a value to a pointer like they would in C, doing that exact same thing in Rust is sort of fraught. And so I wanted to make a crate for our programmers and now for other people to hopefully help alleviate a bit of that in the meantime. And I think, you know, ultimately the dream would be for the, you know, Rust language and standard library to evolve to a point where the APIs that Presser provides are provided directly by the language and or by the standard library, so that it doesn't have to be in a library. But as of now, in stable Rust, this is sort of like a way to get benefits early and sort of explore API possibilities.
You know, talking to you reminds me how dangerous it is to actually use a computer again. I forgot how much virtual duct tape there is in all these machines.
Oh, yeah. Oh, absolutely. It's extremely cursed and fraught, and truly a miracle that things work, honestly. But it's also, yeah, I think it's fascinating to think about and talk about.
I feel like I look at a computer like how a doctor interacts with a human. You know, like when you go to get your checkup, the doctor will fling you around like you're like a rag doll, and
Yep,
okay,
yep.
cough here, do this, and I do the same thing. I'm like, all right, stick this USB in there, or rip this screw off, and insert this hard drive. I feel about the same.
Yeah, I mean, it's a good analogy. I mean, like, the levels of cursedness that exist in computers are just like unbounded, it feels like. Oh my goodness. And I think that's one of the reasons that we have to talk about things from like a sort of high level theoretical point of view. Like what I was talking about with the Rust virtual machine is a concept that I think Ralph Shung, who is like one of the primary contributors developing Rust, sort of like unsafety story at the moment. He's the creator of Miri and Stack. Well, actually, not creator, but current lead developer of Miri, which is like a sanitizer sort of for Rust unsafe code. In any case, like, I think that the point of this is that, like, because there's so much cursedness at every level, in order to try to extract performance out of things and for many, many other reasons, like, it only even really makes sense to talk about program behavior in terms of, like, what happens if we create a valid program. Because if we create an invalid program from the language's perspective, then, like, so much cursed stuff can happen. So yeah, I think that's another reason why it's really important to talk about things at the sort of language level rather than the like, what does the hardware do level? Because what does the hardware do like has no meaning if we can't even define, the stuff that comes on top of it. Yeah.
Yeah, I was just thinking about how complicated all this stuff is, and then I was just thinking about how I actually took some time to see what the metaverse looks like from Facebook, and I wonder how you can pour billions of dollars into something and it looks like that. No reason to dig, but I'm starting to think like maybe there's just too many small things to have to deal with, like this memory issue, which should be dead simple, seems is not so simple after all.
Oh, absolutely. I think that's true of many. I think it's similarly in sort of like the Twitter situation that's developing. I've seen many people that are SREs, reliability engineers, posting about how, like, yep, and there's been memes about this for however long where everything is held up by like duct tape and prayers, right? Like, and that one load bearing, server that lives in a shoebox somewhere. And yeah, and in terms of the metaverse, I mean, I think there's probably many reasons for that being the way it is, some of which are certainly technical, some of which are certainly not technical and are likely much more about management on sort of both people management and project management levels. Yeah, I just think that the sort of projects that tout themselves as trying to be a metaverse, at least so far, have come at it from a sort of completely flawed direction of the perspective of trying to extract value first. Like the point of the metaverse is to extract value. When if a metaverse, takes off or exists, it's not going to be because it's an opportunity for investors to extract value out of users. It's going to be because it offers users a compelling experience that they want to participate in. And so it just feels to me like, especially, Meta, Facebook's metaverse project is sort of like the opposite of that. And I think projects like, for example, VR chat or Roblox, I mean, to some degree, the project that we're working on at Embark could be considered a metaverse. I think we're absolutely not sort of billing it as one. And we're making it just to be a fun experience. That's the point of making it. And I hope that future projects, I've seen some other ones as well, and I think future projects in this sort of area should try to be that first rather than a vehicle for investment and monetization, because I think that's doomed to fail from the start in many ways.
So is that what Embark is doing? Is making some sort of metaverse now? Are you letting it slip out?
We should not take that as me confirming that, no. And yeah, I can't say too much more. What I can say is that we're creating a place where people can come together and create things with their friends and play and, both create experiences and play experiences that their friends have created and have a social experience and do all of that without needing to know programming. And yeah, we want to really inspire people to be creative and not just from perspective of pure creation, but creation as play. And that's what we think is really special about our project. And that's about all I can say at the moment. But we do have a recent blog post which essentially says that, but we're also going to be doing a closed test soon. So if you want to check out that blog post and see more of what we're up to, that would be really cool.
Yes, you sent me the link. I'll try to remember to put it into the notes for this episode. It sounds pretty interesting. So you claim that you don't need to know any programming to somehow, I'm going to use the word program or alter this world you guys are creating. Isn't that
Yeah,
right?
yeah, exactly. We are building a world where you can create things as part of the experience of playing, and we want it to be like a creative sandbox environment where you are using both tools we provide and your own things to create new creative experiences that maybe no one has ever thought of before, and to experience those things with your friends.
It's a pretty bold, but also very open and general commitment. So I hope it works out.
Yeah, yeah. I think it's super exciting, and it's really exciting for us to be able to at least say a little bit about what we're doing and share a little bit of what we're doing. And also just to be clear, Embark is working on multiple projects in parallel at once. What I've just been talking about is our sandbox project, our creative sandbox platform, as yet unnamed but announced. And we also have two other games that have been announced, the finals and Arc Raiders. And both of those are quite different and are actually being made primarily in Unreal Engine. The Creative Sandbox project is the one that is using Rust from the ground up.
Yeah, so they're actually been announced. I just went looking on your website just before we have our session. I didn't see any. I see. Okay, to the finals, right? This is what you're talking about. This is the
Yep.
one of the games.
Yep. Hmm.
Yeah, but when you say you're using Unreal Engine, I think everybody in the Rust community feels so sad. Like, hey, man, we're looking for 100% Rust game from you guys.
Yeah, well, I think thinking about exactly what I can say here. I mean, I think, you know, we at Embark, like we are very much like have a shared vision between all our projects to sort of push the bounds of what various different kinds of experiences can be. And I mean, the reality is that we were not going to be able to create an Unreal Engine competitor within a few years. And so our other two game teams, our graders and the finals, are using existing tools and they're still, as sort of a base. And they're absolutely still pushing boundaries of what Unreal Engine can do, using a fair bit of custom code in various different areas, but not Rust through and through.
Are you guys using Rust with Unreal Engine also? Because I know you can do it, but it's not easy.
As far as I'm aware, not directly in like gameplay code. I think we've written some tooling in Rust for Unreal Game Engine game projects and some server side tooling, some libraries that may maybe get used, but nothing that's like, we don't directly use Rust to write, gameplay code or engine code in Unreal.
All right, this is exciting stuff you guys are working on, and I had no idea about why pressure would be useful, and it makes a lot more sense now. I'm glad you took
Awesome.
time to slowly explain and maybe re-explain because my mind just takes time to understand. This is just
No, absolutely. It's complex stuff, and I'm glad to talk about it. Yeah, I'm sure there will be much discussion. And there was good discussion in sort of a Reddit thread, and yeah, like I said, some of the stuff we talked about is still being discussed on the sort of Rust language level. There's repository that's part of the Rust language called the Unsafe Code Guidelines, and in the issues there, there's active discussion about what should and shouldn't be considered valid, both in safe and unsafe code. And so yeah, if you're someone that has an opinion about these things, you can add to the discussion, or if you're someone that wants to learn more, that's where to learn about it.
Okay. And maybe, do you have a link to that? I can put it into the notes.
Yes, absolutely.
Okay, maybe I can put that into notes. It sounds a pretty exciting topic. I'm that weird person that likes to read about every weird thing and then like talk to people like, hey, did you know that, I don't know, ice cream is made from the devil? You know, some really weird fact for no reason.
Oh, absolutely, yeah.
So I'm
I
sure
do the
I'd get
same.
into this. Yeah. Awesome. Thank you for your time and explaining and actually creating this great. And thanks to Embark for letting you guys open source it. I'm sure this will be helpful for a lot of people. And I'm guessing for somebody like me, it's probably going to be very useful. I'm sure I'm not going to need it now, but then when I do need it, it's going to be perfect. This kind of project.
Yeah, I think that's the sort of library that it is. And yeah,
Exactly.
thanks so much. I hope it is useful for people.
Great. Again, thank you for your time and hopefully have you guys back on again in the future. We want to hear explain the very first AAA Embark Studios game, all in Rust. I'm waiting for that time.
Yes, at some point in the future, we'll see.
Awesome.